Anyhow, I can say now, before maybe some more people come, that my main goal, at least the beginning of the lecture, maybe the most part of it, is about the classification theorem for compact surfaces. Before I present the proof will be based on the Morse theory, certainly. I can say that this is a very classical theorem, and actually it has several different statements which are in reality equivalent, but the equivalence itself is also a geometric result. So the theorem can be proved for topological surfaces, which means a compact topological space connected, and plus every point has a neighborhood which is homeomorphic to a domain in the plane, say to the plane itself or to the open disk or whatever. And for such objects, the theorem says that every topological surface is homeomorphic to, well, I will formulate to what, but you may remember. The maybe more popular statement, which was proved approximately 100 years ago, is about triangulated surfaces. I do not know whether you know what triangulation is, and if you don't know, then I will not explain this. Just surface which is made out of triangles, which are attached to each other by sides, by edges. And again, it is a surface which also has its definition, and then this surface is, as people say, PL, piecewise linear, has a piecewise linear isomorphism to several standard objects. We will prove here, which is natural because it is a course in differential topology, we will prove here the differential version of the theorem. That is smooth two-dimensional manifold. Smooth, compact two-dimensional manifold, possibly with a boundary, connected. Then it is diffeomorphic to one of the surfaces which I will list now. S, G, M, H is obtained from a sphere. This is a piece of a sphere by attaching G handles, which looks like this. M, Möbius bands. It is not possible to make a reasonable picture in three-dimensional space, but the meaning is that we drill a hole and attach a Möbius band whose boundary is a circle to the boundary of this hole. And the last operation is drilling a hole. So we take a sphere, we attach G handles. There's G here, if you don't know. Actually, it's the abbreviation of the word genus, and it comes from basically algebraic geometry. M is the number of Möbius bands attached, and H the number of holes. There is a relation between different surfaces S, G, M, H. They may be diffeomorphic to each other, even when G, M, and H are not the same. We discuss this last time, and we will discuss this later today. But now I formulate my theorem precisely as it has been formulated. That is, every compact, smooth compact, connected to the metal manifold is diffeomorphic to one of these surfaces. They may be called classical surfaces. Okay? Now you can easily understand how the Morse theory can be applied to proving this theorem. So M is a two-dimensional, a compact, connected, two-dimensional and I want to prove that this is diffeomorphic to some S, G, M, H. So what I do, as usually done in the Morse theory, I fix a Morse function on M, which is, as we discussed last time, is constant on the boundary, if there is a boundary, which is less than this constant inside the manifold, the interior, and which for which also our usual property that all critical values are different holds. So we have finitely many critical, non-degenerate critical points, and critical values are all different. And then, according to the main theorem of Morse theory, this manifold M can be obtained from nothing, from an empty set, by attaching handles of index 0, 1, and 2, because the dimension is 2. We attach these handles, and every attaching somehow affects the manifold. What we need to prove? We need to prove that if a manifold to which we attach handles, if we attach a handle again and again, handle in the theoretical manifold and handle in the Morse theory, these things may have some visual similarity, but they're not the same. If I attach handle to what? To a manifold, so that each component is a classical surface. S, Gi, Mi, Hi, where I is the number of the component. But I find too many components because it's compact. Then the result will be, again, the union of some classical surfaces. As soon as we prove this, we prove everything, because after we discuss this, after the very first attaching, the attaching handle to the empty set, we get a disk. Now, this disk is S001, the same as a sphere with one hole. And then we attach new handles. By the way, new component can arise. How can it happen? Actually, at some moment, we can attach one more handle of index 0, so we add one more disk, and the manifold becomes disconnected. So after we attach handles, there is a possibility that the manifold will not be connected anymore, because we attach new components. But still, I assume, this is my induction, that after attaching a certain amount of handles, we have a manifold which is whose components are classical surfaces. Then we attach one more handle, and I am going to prove that again we will have a manifold so that every component is a classical surface. And this gives us all, because after all the attaching handles, we get a manifold, maybe disconnected, maybe connected, but every component is a classical surface. So if the manifold is connected, then it is a classical surface. This is even not the scheme of the proof, sort of some frame. Any questions at this moment? This is a very important moment, because then we will do a geometric procedure, and probably you will believe. But this is what we do. What we need to prove. Moore theory gives us this instrument that all we need to prove that if we already have a surface whose components are classical surfaces, and we attach one handle of index 0, 1, or 2. We should discuss how it looks like. If we attach a handle, then again we have a union of classical surfaces, a manifold whose components are classical surfaces. And this is all. Questions at this moment? Questions at this moment? No. Then we need to consider all possible cases. I can be wrong, but I think there are 7 cases to consider. But if it will be 6 or 5, you will forgive me. Even if it will be 8. So, I said, so we have a union of and we attach a handle. There are 2 very trivial cases. First, what happens if we attach a handle of index 0? Very funny case. To attach a handle of index 0 in dimension 2 or not, we just add to our manifold a new component. And this component is a disk of dimension n. In our case, a disk of dimension 2, which is actually a disk. So this means that, let this be, say, well, n. Then we have n plus a disk. Disk is a classical surface, so that's okay. This case is very much okay. Now the next case. It's not the next, it's the last case. But I count as number 2. What happens if we attach a handle of index 2? Attaching a handle of index 2 and actually attaching a handle of index n to an n-dimensional manifold always means the same. That we have an embedding of S1. I can say S1 times D0 if you prefer. We have an embedding of S1 into the boundary of our manifold n and attach a disk, if you prefer, D2 times D0. Attach a disk to this circle. So we have a circle in the boundary, but the boundary is the union of circles, right? Boundary of any two-dimensional manifold is one-dimensional manifold. We know that without boundary, compact to the one-dimensional manifold without boundary is a union of circles. So the boundary consists of circles. So just we take one of those circles, which is a boundary of one whole, if it is a classical union of classical surfaces, and just attach a disk to this circle. A very common operation. We remove this hole. So attaching a handle of index 2, certainly it is attached to one of the components because the circle is connected to S, G, M, H. Is possible only if H is not 0, and makes it an S of G MH minus 1. Just removes one hole, which certainly again shows that we are within the class of classical surfaces. These 2 cases are very direct and obvious. And then the handle of index 1, remaining case. This is the case where we need to do some work. It falls into subcases. And in some subcases. We need some work. In some subcases, we don't need really any work. So first of all, what is the handle of index 1? This is the following. We have the boundary of our manifold. These two pieces of boundary, they may actually belong to one component or to different components, but just two pieces on the boundary. And then we take intervals and make attaching like this. So we take a strip of paper, put some glue on the short sides, and attach them to the boundary. Okay? Now, I said that there are cases, and there are some cases. I think there are 5 cases. 5 geometrically different cases. And we need to understand what happens for every of these cases. Case 1 and case 2. We have just one circle in the boundary. So in particular, it belongs to some component. So the component is G, S, G, H, MH. And then we don't look anywhere else. We attach to this circle a strip. And this can be done in 2 different ways. And this can be done in 2 different ways. Either we do this, or we do this. It is very clear that this strip, you can twist it, right? So let's guess. So my surface, it was one component. We did not even look at other components. It was S, G, M, H. If we do this, what happens? What do we get? This case is very clear. To attach this strip is the same as to make a new hole, right? So this is the same as we had a hole and we make a new hole, right? So this case is very clear, and what we get is S, G, M, H plus 1. This is satisfactory. It is also a classical surface. What happens in this case? Do you have an idea regarding this? This case is sort of slightly more complicated, but not the most complicated case. I can say that this is, of the 5 cases of attaching handle of index 1, it is second complicated case. You know, you want to say? No, you don't want to say. Well, I can say this. So what do? We take this hole. You understand, do not shadow. I can shadow to make it more interesting. And then what we attach? We attach a collection of diameters, which are all disjoint, right? Very interesting. But not all diameters, only some of them. What if we actually, can happen, we forget to stop and we attach all the diameters? This we discussed last time. This is the same as attaching a Möbius band. But so we attach a Möbius band and then we look at it and we see, well, we attached too much. So we need to remove what we attached without necessity. We remove what? We remove the thing. Right? And believe it or not, it is a disk. So my operation consists actually of two parts, attaching a Möbius band and removing a disk. You should realize when we attach a Möbius band, actually we kill a hole. So if we attach a Möbius band and do not do anything else, we certainly increase m by 1, but we reduce h by 1 because the hole disappears. And then we make a hole back. So this operation gives you S, G, m plus 1 h. You understand? We use our hole to attach a Möbius band. So we get a new, we increase number m by 1, but simultaneously we kill a hole. But after it, we make a hole. To kill a hole and to make a hole means that h stays the same, right? And m becomes more by 1. So this is what happens in this case. This is what happens in this case. You can check, by the way, that if we had a disk and attach, a disk was S, a disk was S001, one hole. And attach a Möbius band in this way, attach a handle shown by, we get the Möbius band that is usually constructed. And Möbius band certainly is S011 because one Möbius band and one hole. Yes, so this is this case. As I said, second complicated. Okay? Proof very geometric, so you certainly should rely at least partially on the pictures. Yes?
So if we twist the band twice, it's the same as not twisting it.
Yes, twist twice is the same from the point of view of topology, is the same as not to twist at all. What we have a strip, we have two short edges, and then we attach them to our two intervals, either with the same orientation or with the opposite orientation. That's only the possibility. If we twist it 2 times, it's the same as not twist at all. Twist 3 times, same as twist 1 time, and the direction of twisting also has no importance. Now, the next 2 cases again. We attach a handle, this strip of paper, to different components of the boundary of the same component. So, now we assume, again we have a surface S GMH, and we consider two different components of the boundary. And we attach, then we take an interval on both, and we attach a handle of index 1, and this can be done in two different ways. First this, so still we have this surface, and then we attach a strip like this, right? And second this. Again, we attach. You understand that there is a surface everywhere. We attach a handle. We attach a handle with twisting. And again, two cases. This one is the the most complicated case. This one is a very simple case. Can we say anything? What happens if we attach a strip like this? Right. We can attach we can attach a whole handle, not just this, but actually we can attach the whole handle. And then we can observe that we attach too much. We remove the thing which we attached erroneously, and this will be a disk bounded by this circle. So this means that we add a handle, but then remove a hole. The fact that we remove a hole also visible because we had two components in the boundary, and after this attachment we have only one component. So what we get is S G plus 1 M H minus 1. Now the most complicated case. Something is written about this case in my notes, about every case. But I thought about it a little bit, just a little bit. And I decided that maybe here in the lecture I will present a different, maybe sort of, how to say, more convincing proof. But first, what do you think will happen if we attach a Möbius, well, a twisted strip of paper to the surface? Just imagine that we have maybe a cylinder. Two, it is important that a component has a disconnected boundary, at least two components of the boundary in this connected surface. And we attach such a thing. We attach such a strange, right? Strange thing. Will we have again will we have again a classical surface? Any guess what can be obtained? So we had S, G, M, H. Let us first begin with the easiest part. What happens to H? H is the number of components of the boundary. If I take this thing, then what do you think can happen to the components, to the number of components of the boundary? We had two, and now we have one, which means, whether we want or not, that we reduce the number of components by 1. H goes to H minus 1. But also we have G and M. Can you guess? You cannot. You don't want to say. Well, it is written in my notes, but I see that you didn't look, so you don't know. But the result is that G stays the same. and m gains 2. We will get a very strange thing. We will get an S G m plus 2 h minus 1. And now, let me explain why. And now let me explain why. Understand the statement? So if we attach a handle as shown in that picture to S GMH, and it is attached with a twisting to two different components of the boundary of this component. We do not even look at other components now. They live their life. So look. This proof is different from what is written in my notes. Certainly also correct. I want to do the following. So two components. And I want to attach a handle like this. Before that, let me remove something. So the first thing which I do, I probably can erase everything because I need some place, some space in the board. So the first thing I do, I remove from my surface this part. Just take a pair of scissors and remove this small segment. To make, this is the most important thing, to make the boundary, the piece of the boundary to which I attach my strip, to make it connected. Is clear? So my surface was S, G, M, H. Now it becomes S, G, M, H minus 1. Very clear that simply of two holes I make one hole, and all the rest stays as it was. Now I want to do two things. First, to attach the strip as it was done before. And second is to put in its initial place this piece which I removed, right? So first operation, I attach this. But now it is attached to a connected component of the one connected component. So we know what happens when we do this. Precisely my previous operation. So this makes it S, G, M plus 1 H minus 1. And then I want to attach this back. What do you think about this? First of all, before this attaching, again I have a hole. Let me trace by my finger its boundary. This way, this way, this way, and back, right? So again I have actually a surface, have one hole. And I take this strip. We already know what happens if we attach a strip to one component. But what kind of attachment is this? Let me try to trace the orientation. So after we attach that thing, let me trace the orientation. So we haven't attached, we still haven't attached this. Let me trace the orientation of this. Go this way, this way, this way, this way, this way, this way, this way. This, this, and this. So when we make this attachment, actually, we attach this to the two pieces which are oriented like this. That is oriented in the opposite way on the boundary of my hole. So this attachment is the same as the attachment of one more strip, which is twisted. You see it? Actually here, because of this, I can draw it differently. Maybe this will seem to you more convenient, more natural. This part, we can twist it back. And this will be this. And then this, so I just take this part and twist it back. And then this attaching is actually this attaching because of this twisting. So the second operation, which finishes my construction, is again the attaching of the twisted. It seems untwisted here because the boundary of my hole is twisted. Again, attaching a twisted strip. And we get S G M plus 2H minus 1. This is a way how to visualize this construction without adding everything, it's just removing. I remove something and then I do not forget to place it back. Okay? So this is, at least seems to me, the geometrically most involved part of the whole proof. What happens if we attach a handle like this? And my proof is almost over because all I need is to consider the last possibility. We have two components of our surface. Hole here and hole here. Better to draw it like this. This is S, G, M, H. This is S, G prime, M prime, H prime. And then we attach a strip like this. What happens? This is very obvious. First, my surface becomes connected. Second, handles on the left-hand side and the right-hand side will be handles on our new surface. The same with Möbius bends. And the holes, out of this hole and this hole, we produce one hole. So what we get is S, G plus G prime, M plus M prime, H plus H prime minus 1. And this is always the proof. So at this moment you can say something, ask something, cast a doubt on something. Do? This is not important because actually we can just take a component and twist it. The orientations of the boundaries of these two holes, since they belong to different components, we cannot compare them. If we have a twist here, then simply rotate the whole surface. I think in that direction. The whole component. And your twist will disappear. No, this is all. So every attaching a handle makes a surface the surface remains union of classical surfaces, which means that every surface at all, every compact two-dimensional connected manifold, maybe with boundary, is an SGMH. Now, I have several minutes left, and this is good. I want to say last time Dale mentioned it, but now I will want to mention it also, that actually it is possible that two surfaces with different GM and H are actually the same. Moreover, actually there is only one relation, which I formulate now. Attaching three Möbius bands is the same as attaching one Möbius band and a handle. Actually, there are no other relations. This I probably will say at the beginning of next lecture, but I say it now. To distinguish, so to prove this, we need to have some instruments to distinguish different surfaces. And we don't have these instruments. There are invariants in topology, which can distinguish classical surfaces as GMH, not related by this relation. They are not diffeomorphic. And I said last time that this can be formulated in such a way that every surface is either a sphere with handles and holes, or a projective plane with handles and holes, or a Klein-Bottle with handles and holes. And neither two of these three series are the same, are diffeomorphic. This is a separate issue, and actually we have no instruments to prove this. I can only provide some hand waving. But for this, I can give you an immediate explanation. We need to consider the Klein-Bottle. I want to say that there are two constructions of the Klein-Bottle. The first is actually the picture book construction, which we take a sphere and attach a handle like this. It is called a perverted handle, an inverted handle. A handle which is attached by the two ends with different orientations, like this. And this is a Klein-Bottle. Klein-Bottle is defined like this. We have a picture of Klein-Bottle, we'll keep beside this, maybe slightly different shape, but basically the same. This is one of the two classical constructions of Klein-Bottle. Another one is you can take two Möbius bands, attach them to each other by their boundaries, and also a Klein-Bottle. Why? A Klein-Bottle also can be obtained from a cylinder by attaching to each other the two bases with, again, different reversing the orientation. It can be done in the following way. This point is attached to this. This is attached to this. This is attached to this. And this is attached to this. Simply this point to this, this to this, this to this, Just we attach the two bases using the reflection of the circle in the diameter. Now take again a pair of scissors and cut this into two pieces, the cylinder. You see how it is done. Now, what are the two pieces? This one. Right? And you see this is a strip of rectangle with two sides attached to each other with the opposite orientation. So this is a Möbius band, and the remaining part is another Möbius band. Okay? So you see, actually, we can take this Klein bottle and make 1 million holes and attach 2 million handles. But a Klein bottle can be obtained in two different ways. First, attaching to each other two Möbius bands. So this is the same as to take a sphere and attach two Möbius bands. Or attach an inverted handle. And now my last remark. Suppose that actually we had a Klein bottle, we had a surface, we attach an inverted handle to a surface which already contains a Möbius band. You see it? Then we can take this base and move around the Möbius band. What happens? It changes its orientation. So I want to say that if you attach an inverted handle to a surface which already contains a Möbius band, then it is the same as to attach the usual handle. That's all. Because you had a Klein bottle plus holes, handles, and at least one Möbius band. One more Möbius band. Which means that the number of Möbius bands was at least 3. 2 for the Klein bottle and one more. And then attaching these two Möbius bands is the same as the attaching of a handle, which is again the same as attaching the usual handle. Provided that my surface already contains you please understand that attaching bands handle operations are the same. They cannot be the same because the first provides a non-orientable manifold, the second provides a orientable manifold. But if my manifold already to which I attach Möbius bands or inverted circle already contains a Möbius band, then attaching two Möbius bands and attaching a handle are the same, which means that attaching 3 Möbius bands or 1 Möbius band and a handle, these two operations are equivalent. This is how it is explained. Now, my friends, at this moment we finish today. So next time, I hope to begin new subject next time. I will make just several remarks regarding more theory. And again, I already said this, I say this again. If nothing very much unexpected happens, then not next time, the time after next time, we will have a test here. I will give you several very simple problems. You will be angry with me that the problems are this simple, but excuse me. You do them, and then next Monday we again return to our subject, my very last subject in this course. Differential forms, integration, Stokes formula, and a little bit of the Ram cohomology. This is what I'm going to speak of. There remains 7 or 8 lectures, I don't remember. Yes, and we will we will discuss this stuff. Thank you.